Yes, I'm Hervé, co-founder of pyannoteAI and chief science officer there. I co-founded this company a year and a half ago with Vincent here at the front row, cheering for me. So anyone knows what speakerization is? Okay, for the others, I hope you're not too scared of this word, and I hope that by the end of this talk, I would have convinced you that this is actually the foundational layer of conversational AI. And not any kind of conversation, not human-machine conversation, but real conversation, human-human conversations. So just a few quick words about me. I used to introduce myself while I was a researcher in academia as the Pyannote guy. That's how actually people know me in the academic field. So I first learned about speakerization in 2012. And this is really where I really fell in love with this problem, machine learning problem, and never really looked back. Since then, I've been working almost exclusively on this particular topic, research-wise. In 2016, like anyone else in the field, I had to switch to deep learning. So I trained my first neural networks. It was focusing on a small subtask of speakerization, speaker change detection at the time. And I really was amazed by the performance that those models could actually achieve with those new neural networks. So that's why I kept working on deep learning for speakerization. And in 2020, I released the first open source end-to-end diarization models. And at that time, set the new state of the art. And since then, people have, there are just a few fun tweets that I copied here, in particular the last one, which is a bit scary, but I'll let you read it if you have time. And in 2024, based on all these experience on the speakerization, I co-founded pyannoteAI. Let's take a step back. So until, I don't know, superintelligence is here, I guess when you feel sick, you'll go to the doctor. You'll actually talk to the doctor about your symptoms, about the medicine that you tried. The doctor will also ask you questions. And about your symptoms, he will probably suggest a few medicines as well. And at the end of his day, the doctor will have to fill this kind of SOAP notes. SOAP stands for Subjective, Objective, Assessment, and Plans. This is the official documents that any doctor, at least in the US, have to fill. And it takes a lot of time for them to actually do this job. So that's why there's a lot of company building AI medical scribe that try to actually automate this. So what they would do is they would record the doctor-patient conversation. Then they would apply speech to text. So they'll get those nice transcription with the symptoms showing up in the words here. And then apply LLM to actually automatically generate those SOAP notes. The problem is that without the actual names or the actual role of the speaker in this conversation, you might actually conclude completely different conclusions, right? Depending whether the speech turns of the doctor are the second or the fourth one, or the last two ones, or even if there's a third speaker here, the result might be completely different. So that's why knowing who said what is just as important as what was said in lots of applications. And that's really the point of speakerization. I'll come back to that later. Other examples of applications where who said what is just as important as what was said is, for instance, video translation, automatic video translation. If you have this content in French and you want to touch a much larger audience, you would have probably to translate those into Spanish, Italian, English. And obviously, making that automatically would be awesome. There's lots of companies trying to do that. And for the actual translated video to be attractive, it's probably a good idea to have a consistent voice for each speaker over the course of the translated videos. That's where speakerization is useful. In the case of meeting note takers, for instance, when you join a Zoom meeting, indeed, there might be just one person in each channel, but now more and more there are hybrid meetings where two people actually join from the same microphone. And to actually know who's in charge of doing this action point that was decided, then you need to know exactly who said what during the meeting. Same, when you have a large audiovisual archive to index, to be able to search, for instance, into large collection of podcasts. It would be nice to be able to track speakers across podcasts, like does this guest appear in the podcast from this host, and this host. And then you can search about anything that, I don't know, Hervé Bredin said in a podcast. There's only one with me, so right now it's easy. For all of those tasks, speaker diarization is really, really useful. Now I come to the actual part, the actual interesting part, I guess, about what is speaker diarization. So it all starts with a recording of a conversation. It can be done after the conversation took place or in real time during the conversation, but the task in itself is the same. So the first thing that you can do with a recording is just maybe detect the parts where someone is speaking and when no one is, or when someone is not speaking. This is called voice activity detection. But this actual, the information that it gives is probably not enough to really understand the conversation even better. So the next step is probably to segment those long speech regions into smaller single speaker speech turns. This is what we call segmentation. So you can see in this example here that it would actually detect speaker change point as well as crosstalk. So when in natural spontaneous conversation, people will say yes, okay. Those are called back channels. And they are very frequent and sometimes may convey the most important information in a conversation. Like if you're asking a question, a very critical question to someone and they answer yes while you're still speaking, you don't want to miss that. So that's the point of segmentation and being able to actually detect those crosstalk. And obviously the next step then is to assign each speech turn to the right speaker. And this is really what speaker diarization is. It includes both voice activity detection, segmentation, and then speaker diarization. So at the end of the speaker diarization pipeline, you get this nice set of metadata, timestamps with the start time, end time, who said what. No, not who said what, but who spoke those words. And the tricky part about speaker diarization is usually you have no prior knowledge about the conversation. You don't know the number of speakers. You have to estimate that automatically. And you don't even know their identity, so they can't be part of the training set. You have to build systems to recognize speakers that were never part of the training set. So that's one of the reasons speaker diarization is a tricky part. As you said as introduction, that STT seems to be a solved problem today. So why is speaker diarization so difficult? And it shouldn't be that difficult. So I am trying to actually compare speech-to-text and speaker diarization and highlight the differences between those two tasks in this slide. So the first thing that we need to be aware is that those two tasks are completely orthogonal. For speech-to-text, you want to be as independent to the speaker as possible. Whether I say bonjour or someone else say bonjour with a different accent, you still want the output to be bonjour. So you have to be robust to variability in the speaker identity. While on the speaker diarization part, it's completely the opposite. Whether I speak English ou si je parle français, I still need to be tagged as the same speaker across the conversation. So this is completely text independent. You can't rely on text to achieve speaker diarization. You could, but that's another story. And for the same reason, speech-to-text is usually trained for one specific language, or now there are multilingual models as well, but it's still a fixed set of languages. If you want to add a new language, you have to retrain the model. For speaker diarization, it is generic and language agnostic from the beginning. We train it based on the actual sound of the speaker voice and not the actual words. So those are the main difference between speech-to-text and speaker diarization. And now I'm coming to the part where I try to highlight why this is actually much more difficult than speech-to-text. The first thing is that speech-to-text historically has been really trained to solve the single speaker problem, where someone is speaking, there might be some stuttering, there might be some hesitation, but still it's a long stream of words from the same speaker. While for speaker diarization, actually by design, we want to handle multiple speakers, interrupting each other, as I said, back channeling, very fast interactions, and so on. So that makes the training much more difficult. And another example which is related is the fact that, to train a neural network to do speech-to-text or speaker diarization, you have to collect training examples. For speech-to-text, you can see a training example as just one word. You have, the audio corresponding to one word. You train your model to take a piece of audio as input and return the word that corresponds to it. For speaker diarization, one training sample is the whole conversation. I did a few estimation, let's say a 10 minutes conversation where we speak, in average, people speak at 4 words per second without interruption. So it means that to gather one training sample for speaker diarization, you have to have 1,000 more audio, longer audio than for gathering one training sample for speech-to-text. So that's one of the reasons, the main reason why speaker diarization is not solved yet. And the final thing that I wanted to highlight regarding this particular aspect of why this is difficult is that diarization is not your usual machine learning problem. Let's take this example of a prediction of a diarization system on a conversation. So it finds 2 speakers, the green one and the blue one. If I give you that output as well, it's actually, for the speaker diarization task, equally valid. We just simply switch the labels of the speakers. But those outputs are completely correct as well. If we go a bit deeper in this, let's say you have a conversation between 2 people first, between the speaker, the black speaker and the gray speaker here, and then between the same black speaker and the green speaker. So the speaker diarization could assign speaker label 1 to the black speaker in the first one, and then 2 to the gray one. For the second conversation, that's fine. We can say that speaker 1 is the black one and speaker 2 is the green one. But what should we do with that one now that we have 2 speakers to assign, and either we change the label for speaker, the green speaker, or for the gray speaker. And what I mean by that is that the classes that is assigned to each speaker are dependent on the other speakers in the conversation. So that makes training those models very difficult, and not in the usual way that you expect, like a dog classifier or an animal classifier and this kind of stuff. So now I'm reaching the point where I would like to make a demo. So brace yourself. I asked ChatGPT which tool I should use to actually do this demo. And surprise, they offered to use Pyannote Audio, so that's convenient. So a few words then about Pyannote Audio. So this is an open source toolkit that I've developed over the years while I was a researcher at CNRS. So it's MIT license. The code is available on GitHub. There are open models on Hugging Face. And I just wanted to highlight the popularity of this thing. It kind of got out of control. So basically on GitHub, it has 8,000 stars. Here you have the monthly, I think it's the monthly, no, daily downloads from PyPyStats of the Pyannote Audio toolkit. So it's around 30,000 daily downloads as of today. So this is for the code part, and on the right you have also the pre-trained neural networks that are shared on the Hugging Face platform. And we also have some nice stats here. So for instance, the latest speaker diarization pipeline is downloaded 16 or even 17 million times every month, at least in the last month. There are a bunch of fine-tunes, 32 fine-tunes model, and we also know that there are around 100,000 unique registered users of Hugging Face who requested access to this speaker diarization pipeline. And another interesting stats, if you filter all the models on Hugging Face having in common the audio tag, you'll see that the five most downloaded models are all from Pyannote, just in front OpenAI Whisper, and a bit down the line there are some speech-to-text models from Meta as well. And those, I don't know if any of you ever use WhisperX. Basically, if you use WhisperX, you actually use Pyannote Audio already, maybe without knowing, because Pyannote Audio is a dependency of WhisperX, and it's the one that provides the speaker diarization part of WhisperX. So basically, Whisper gives you the words, and diarization will, Pyannote will give you the speakers. So over the years, I wanted to show you the current state of the art of diarization so that you get an idea, because I kept saying that we are not at the level of speech-to-text yet. So depending on the difficulty of the task, each group of three here are three different domains. So the one on the left are in the wild YouTube videos, while the one on the right are TV news where people behave very nicely, don't talk on top of each other and everything. And you see that the open source toolkit diarization error rate, so lower is better, can go from 30% wrong to as little as 8% on the right. And I wanted to highlight the fact that we just released at pyannoteAI our second iteration of our flagship speaker diarization model called Precision 2. So it was released beginning of September, and it brings a really nice improvement compared to Precision 1 and our first edition, as well as obviously the open source toolkit. And this improvement that we brought from Precision 1 to Precision 2, we are actually about to release it end of this month, if all goes well, to the open source toolkit with a new model that we call Community 1. And basically, I'm going to make a demo here. That's nice. I have 2 more minutes. That's perfect. So basically, just here a few, you'll see the code right after that, but basically, how do you get speaker diarization out of Pyannote Audio Community 1? It's just 2 lines of code to instantiate the pipeline. So basically, it will download the models from Hugging Face. Then 1 line of code to actually process the conversation that is pre-recorded here. And then the last 2 lines are basically just printing the results. So let me try a demo. And I'll need the sound at that time. Hopefully it's fine. So here I have the usual conversation that I'm using for all the demos. So it's a conversation between 2 women over the phone.
Hello?
Hello.
Oh, hello. I didn't know you were there.
Neither did I.
Okay, I thought, I heard a beep. This is Diane in New Jersey.
And I'm Sheila in Texas, originally from Chicago.
Oh, I'm originally from Chicago.
So this is the reference annotation. This is what we expect from a perfect speaker diarization system. And so I'm going to show you how you can achieve speaker diarization using this new model that we're going to release later this month. So as I said, the first 3 lines is basically instantiating the pipeline. Then, because I'm on my Mac, I actually send this pretend pipeline to the MPS device, but it obviously works with CUDA and CPU, if you want. And then I will process the file. So right now it's running on my Mac. It's finished. It's only a 30 seconds audio file, so it's very quick. And here I'm showing the actual output of the model on this specific file. So the first line is the regular speaker diarization. The second line is what we call exclusive speaker diarization. Basically, you see that we removed all the overlapping regions here to make it easier to reconcile with speech transcript. And I just wanted to demo quickly that with just 1 line change of code here, you can actually tap on our API and switch to Precision 2 model. So same, right now what's happening is that it's going to the cloud. I'm sending the audio file to the cloud. It's running, hopefully, if all goes well. No, it won't work because I'm not connected. This I forgot, or maybe it did. It did. So let me then just show the difference between community 1 at the top row and precision 2 at the bottom row. Maybe just playing the first part so that you understand that the second one is actually better.
Hello?
Hello?
Oh, hello. I didn't know you were there.
And but you get the idea. It's almost perfect. So I'm done. Going back to my final slides of presentation. I hope now that I have convinced you that speaker diarization is the foundational layer of conversational AI, and yeah, happy to answer your questions.